Okay, here we are going to see some. In the previous class, we have seen some of the examples of iron-sulfur cluster. Usually they exist in the metalloproteins, and those proteins play roles in electron transfer unit. In this slide, I'd like to show you how those kinds of iron-sulfur cluster can be prepared. You know that inorganic chemists are quite interested in preparing replicative models, and they always want to synthesize the biomimetic things. But the iron-sulfur cluster found in proteins cannot be prepared easily because of the redox reactions and the polymerization reactions here. For example, uh, it may be very simple if we can prepare iron-sulfur cluster by just mixing iron and sulfur. But if we react ferric iron with thiolates, the ferric will be readily reduced to ferrous, and there will come disulfide bond. It means that there's no direct bond between sulfur and iron easily. And also, even though there comes iron sulfur coordinate bond, they do not exist as one ion, one sulfur, or two ion, two sulfur cluster. They make polymerization. But after a series of trials, the inorganic chemists found the methods how to prepare ion sulfur cluster. This is reaction 5. Here, they utilize ferric chloride and NHHS and the three equivalent of thiophenols. Here, the first, in the first, they prepared ions, ion sulfur coordinate complex, and here the R group is something with phenyl. Due to the steric hindrance, the polymerization reaction 4 did not occur. And then, when some amount of NaHS and methoxide is added, there comes the cluster of iron sulfur. Here, some of the thiolate ligands was consumed to reduce half of the ions. So the starting ions were all Fe3 plus, but in the final one, there was a mixture of Fe2 plus and 3 pluses. And there was another trial to prepare iron sulfur cluster. Here, the elemental sulfur was utilized along with thiols. So here, as you can see, the ferric chloride and thiolate and sulfur react together to make iron sulfur cluster, and some thiols are oxidized to reduce a part of iron 2 plus, iron 3 plus to 2 plus. You can see here the starting chemical was FeCl3, ferric chloride. And when there was excessive thiolate, first there comes Fe sulfur coordinate bond. And remember that here the alkyl should be bulky so that the iron sulfur ion polymerization can be avoided. Then the addition of elemental sulfur makes iron sulfur cluster. Here we will see the core extrusion technique based on the cluster chemistry. Here the reaction 7 and 8 shows how the bioinorganic chemist extruded the iron sulfur cluster from the protein. Suppose that this is the iron sulfur cluster unit inside the protein. When we add excess amount of thiols, the thiol here with R prime and thiol here with R can be replaced. So here these thiolates are from the proteins and these thiolates are from the solution. If this thiolate and this thiolates are exchanged, this iron sulfur unit can be detached from the protein. Here is another example for the 2 iron 2 sulfur cluster. Also these thiolates are tethered to the protein part and these thiolates are from the solution. So the exchange between solution thiol and the protein thiol result in the extrusion of iron sulfur cluster from the protein to the solution part. This reaction is called core extrusion. So in one line it can be prepared like that. The hollow protein plus excessive amount of thiol in the unfolding solvent unfolds the protein and extrude the core part of the metal. And there comes apoprotein. The terminology holoprotein means the protein having the metal part, and the terminology apoprotein means the protein without metal. Okay, then let's study the polyiron oxo clusters and the biomineralization. Polyiron oxo cluster is one of the example of biomineralization. You know that inside the body, the iron is well utilized in various aspects. For example, the iron is found in hemoglobin, the dioxygen transport system, and the iron is utilized as the catalytic center or electron transfer unit. Most of the ions there are coordinated, but not all the ion exists as a single Fe3+. Some exist as the polyiron oxo cluster. For example, this is the dinuclear iron oxo core. Here, the 2 ion, 2 Fe3+, is linked with the oxygen. The oxygen is a bridging ligand between 2 ions. It is well known in the hydrolytic chemistry of iron 3+, and also formed when iron 2+ compounds are oxidized by dioxygen. Here you can see that when Fe3+ reacted with enough amount of base, they are hydrolyzed to make iron oxide. This iron oxide is not the iron oxide core. This is a kind of solid state materials in which iron and oxygens are linked in three-dimensional way. And some iron 2+ are also oxidized in the presence of water to give iron oxide. So these kinds of reactions are very spontaneous and well known in the hydrolysis chemistry. So the biological system takes disadvantages to get the iron oxide cluster. The similarity between this iron oxide core and this iron oxide compounds is the bridging ligand of oxygen. And the metalloprotein hemeritin, hemeritin is a kind of oxygen transporting system in marine invertebrate. And they have iron oxide cluster. And also in ribonucleotide reductase, there exists iron oxide cluster. The oxygen here act as bridging ligand, so we put the nomination, the wording mu, to say that oxygen is a bridging ligand. Mu oxo diiron moiety exactly says this one, iron oxo core. And this mu iron oxo moiety in the hemeritin and ribonucleotide reductase are linked by one or two additional bridging carboxylate groups. I will show you the bridging. So here, basic metal carboxylate. Look here. Here there are three ion cations, and oxygen bridges, and one oxygen bridge, and six carboxylate bridge, and some of the ions are also coordinated to ligands. Here you can see here, this is the basic metal carboxylate, but this is found in the chemistry, but not in biology. Look, the metals can be Fe3 plus. The three Fe3 plus are bridged by one oxygen. Oxygen can bridge to two ions, and also it can be bridged to three ions. And there are 1, 2, 3, 4, 5, 6 bridging carboxylate. As you know, the carboxylate has two oxygen center, so it can be coordinated not only to one ion but also to two different metal ions at the same time. And also there are some more ligands coordinated to the metal center. In this way, all the three metals are stabilized in the octahedral geometry. You can see all the metals, the ions, have 6 coordination, and the geometry is octahedral. And you can see here, the B is a carboxylate bridged diion unit in hemeritine. We have seen this structure already in chapter 1. Here, the oxygen, in fact, this oxygen is OH, is bridging the two ions, and the two carboxylates are also bridging the two ions. Look, this is a kind of analog to this one. One difference is that there exist two ions in hemeritine and there exist three ions here. Look at the example of C. The carboxylate bridged ion unit in dioxide R2 protein is ribonucleotide reductase. Here there is bridging oxygen and bridging carboxylate from the glutamate amino acid residues. Anyway, all of these examples show that ion is stabilized in octahedral geometry with six ligands. Here only this ion is 5 coordinated. It's why this hemeritine ion is affinitive to the oxygen. When there comes oxygen, the 6 coordination of ion is satisfied. Okay, here we will see some of the extreme example of ion storage protein. The name of protein is ferritin. Ferritin contains many ion oxo clusters. In fact, ferritin is a kind of ion storage protein. So it can store large amount of ions utilizing the coordination bond. There are some features of ferritin proteins. Here, it consists of a protein shell of 24 subunits surrounding a core of hydrated ferric oxide. Fe2O3 is ferric oxide, and the hydrated iron oxide is surrounded by the ferritin. Each protein subunit consists of 175 amino acids, so it is not a very big protein. And the apoferritin can accommodate up to 4,500 ion atoms. Apoferritin means a ferritin without metal, without ion. It can accommodate up to 4,500 ion. This is a tremendous, very big value because one ion per amino per one amino axis is possible in this ratio. And the overall structure of the protein is very highly symmetric. The structure is roughly spherical. The outside diameter is 130 angstrom, about 13 nanometer. The inside diameter is 75 angstrom. So it's a kind of shell structure. And the inside shell, the outer shell is made by protein, and the inside there exists the ferric oxide. There exists four-fold channels that are lined with hydrophobic residues, and there is a three-fold channels which are lined with hydrophilic residues like aspartate and glutamate. This point is quite important. There are two types of channels in ferritin. One is lined with hydrophobic residues. It means that these channels are not utilized for the passage of hydrophilic moieties like water, iron oxide, hydroxyls, and etc. And this channel, the threefold channels, are hydrophilic. So ions, oxygens, waters, some other ligands like carboxylate can be transported passed through this channel. The inside of the protein shell is also lined with hydrophilic residues, so that the inside inside of the shells is affinitive to hydrophilic iron oxide. Look, this is the structure as a somewhat, how can I say, spherical, and here each colored things are subunits. This is one subunit, this is one subunit, this is one subunit, and this is one subunit. And you can see a channel here. Here there is a channel, and it is surrounded by 1, 2, 3, 4 subunits. It's a four-fold channel. And here is another channel, and it is surrounded by 1, 2, 3 subunits. So this channel is threefold channels. This is hydrophobic channel, and this is hydrophilic channel. And this is a cross section. You can see the thick walls. Inside, it is covered with hydrophilic residues, so the hydrophilic iron oxide can be stored inside. Here, this is more schematic diagram for the ferritin, apoferritin, ferritin without iron moiety. Here is threefold channel, the hydrophilic one, and here is the hydrophobic chain. When we magnify the hydrophobic chain, there exists repetitive leucine residues on the alpha helixes. Leucine has methyl group, so this channel is hydrophobic. But here, in the threefold channel, there exists much of carboxylate and hydroxyls, so that the channel is hydrophilic. Inside the ferritin, there exists an iron core. It's not a perfectly iron oxide. It's a kind of hydrated iron oxide. It's more like cluster. So iron in the cluster, the iron is octahedrally coordinated, and those ions is joined by bridging oxide or hydroxide ions. The ion oxygen distance is 1.95 angstrom. It's around 2 angstrom, so it is a kind of tight coordination bond. And the ion-ion distance is 3.3 angstrom. So there is no direct bond between ion and ion. And approximately 7 ion neighbors at this distance. So the point of one ion, the first coordination shell is covered by oxygen, 6 oxygens. Some oxygens are bridging oxygens, hydroxyls, or are possible. And in the second shell, which has the diameter, the radius of 3.3 angstrom, is composed of ions, and it's a close-packed array of oxygen atoms with ion atoms partially occupy the octahedral interstices. The vacant octahedral sites may be arranged irregularly. The vacance effect is possible in biological systems because, of course, in solid-state chemistry, in the nature, the iron oxide has vacant site effect. But anyway, there exists a vacant site, and it is arranged irregularly. The formation of the ferritin core, the iron oxide, is one of example of biomineralization. The most well-known biomineralization is the formation of sea shells or pearls in the shells. The sea shells are calcium carbonates and calcium carbonate mineral, and these calcium carbonate minerals are produced inside the biology. So it's called biomineralization. Also, the egg shells, which is also a kind of calcium carbonate, calcite, is formed by biomineralization. Our bone, our teeth are minerals made of hydroxyapatite or apatite, uh, apatite chemicals, and the formation of bones and teeth are also biomineralization. And another example is the magnetite particles made by magnetotactic bacteria. They produce small nanoparticles of iron oxide through biomineralization. And let's look at the pathway of the biomineralization for the ferritin core. Iron 2 plus into the hydrophilic channels or to the edge of the interior. So iron 2 plus can get into the protein through the hydrophilic channels. And the iron 2 plus is oxidized to iron 3 plus by aerial oxidation, and there comes some initial complexes, small coordination compounds of iron oxygen, and they grow through hydrolytic polymerization of iron 2 plus with concomitant oxidation of iron 3 plus to produce the core. And this is that core. Look, the structure is a little bit different from iron oxide. The iron oxide with the name of magnetite or maghemite. But anyway, they are not a single molecular iron oxygen coordination complex. They are clustered. Here, now one ion is coordinated by 6 oxygens. For example, here there are oxygens, here oxygens, oxygen, oxygen, oxygen. Some oxygens are breaching ligand. For example, here this oxygen is breaching by 6 ion. But this oxygen is from the is linked to carbon, so it may be from other ligands, or some are bound to water and some are bound to hydroxyls. Anyway, this is the structure of iron core, iron oxide core in the ferritin. Yeah, in fact, this is not the real iron oxide cluster inside the ferritin. It's a kind of analogs. And in fact, this is an artificially prepared one. This was prepared by the slow addition of dioxygen to ferrous acetate and methoxide in methanol. In methoxide solution or acetate solution, the hydrolysis reaction occurs very slowly, so that the controlled reaction of coordination bond is possible, and this kinds of small cluster can be prepared. Okay, then let's move to some kind of specialized units. Specialized units for the coordination, to coordinate metals. Throughout this chapter 5, we are studying how the biology can select certain metals and uptake a certain metal. In the uptake process or storage process, there always comes coordination chemistry. Of course, biology produces several kinds of specialized ligands to stably coordinate metals. Some are simple ligands from amino acid residues like carboxylate from glutamate, imidazole from histidine, or some are specialized units like chelates. You know that the porphyrin exists in the hemoglobin. This is not a part of protein. This is not a part of amino acids, but this is utilized to stabilize iron and the hemoglobin. You can see that there are 4 nitrogen centers. The porphyrin itself, when we buy porphyrin from the reagent vendor like Sigma Aldrich, it has this structure. There are 2 nitrogen center in pyrrole center and 2 nitrogen which are uh, hydrated. Anyway, all the nitrogens have 3 bonds, so there exists 1 lone pair electron. And this lone pair electron can directly coordinate it to the central metal ions to give 4 coordination in square planar geometry. Of course, the other 2 ligands can be provided from atmosphere or from the amino acid residues. The metalloproteins can be anchored to proteins either directly or through covalent bonds to the substituent on the pyrrole ring in the porphyrin, or through ligands binding to the 2 available axial coordination position above and below the ring of the macrocycle. And due to the chelate effect of porphyrin, the metals in the porphyrin center are thermodynamically stable. This is another unit which is called chorin. It looks like porphyrin, but there is lack of carbon here. Chorins are comprised of 4 pyrrole rings in the form of a macrocycle, and it is utilized to stabilize the metal center in the 4 nitrogen atoms. They can be coordinated to a metal in an approximately square planar. Due to the lack of carbon here, it is not perfectly square, so it makes approximately square planar. In fact, the absence of methyl carbon atom here is a feature that distorts the geometry of the metal center. So nature and biology intentionally choose chorin or porphyrin to make perfect square or somewhat distorted geometry. This chorin ring is found in vitamin B12. In vitamin B12, cobalt is coordinated here, and that cobalt is also tethered to the vitamin through the axial coordination. Okay, this is metal-nucleotide complexes. It means that nucleotide also acts as a specialized unit to stabilize metals. There is an example of magnesium 2 plus complex. Polyanion is required as a substrate for phosphorate and nucleotidyl transferase enzymes. Magnesium, calcium, sodium, and potassium complexes of ATP are important substrate for ATPases. And this is an enzyme that catalyzes the hydrolysis of ATP to produce the energy. Look here, here the magnesium 2 plus nucleotide complex is found here. The nucleotide coordinated to magnesium by these 2 methods. This beta gamma magnesium ATP, the magnesium is coordinated to beta and gamma phosphate. Here, this is alpha phosphate, this is beta phosphate, and this is gamma phosphate, starting from the end of sugar ring. Both oxygen from the beta and gamma phosphate can coordinate it to the magnesium, and the three alpha, beta, and gamma act as a coordination. In any way, the ATP coordinated to magnesium to be act as a substrate for phosphoryl transferase or nucleotidyl transferase. Okay, another specialized unit is molybdenum binding cofactor. Throughout this chapter, we have seen the example of iron-sulfur cluster for electron transfer unit, but the redox ability of iron lies only on the iron 2 plus and iron 3 plus. Sometimes very powerful electron transfer unit is required, like molybdenum. Molybdenum 6 plus can be reduced to 4 plus. So one molybdenum has a power of 2 electron transfer. So although the molybdenum is not usually found in biology, but it has high capacity in electron transfer unit. So the electron transfer from molybdenum 4 plus and 6 plus is involved in the oxidation of sulfur. In fact, this molybdenum is found as a cofactor. There exists an iron molybdenum cofactor, and this is found in the enzyme nitrogenase. Here, the nitrogenase protein contains both iron and molybdenum as a metal center. And another cofactor containing molybdenum is oxotransfer chemistry, like reductase, oxidase, and dehydrogenase. This is the structure of iron molybdenum cofactor in the nitrogenase. Here, this is a more schematic structure. You can see that there are 1, 2, 3, 4, 5, 6, 7, 8. Let me see, Hannah. 1, 2, 3, 4, 5, yeah, 6, 7. 7 iron and 1 molybdenum. And like in the iron sulfur cluster unit, ions are usually coordinated to sulfur, and there exists molybdenum. And this molybdenum is not only coordinated to the bridging sulfur, but also to the carboxylate or oxygen. Here, the molybdenum is linked to iron through sulfur. So this molybdenum can act as a cofactor prostatic group in electron transfer of the main iron sulfur. And this is possible structure of molybdenum cofactor in the oxide transfer reaction, different molybdenum cofactor. The molybdenum may be coordinated to two sulfurs. Here we can easily catch the importance of sulfur in the stabilization of iron or molybdenum, because molybdenum and ions are iron 2 plus are kind of soft axis. They can be more stabilized to the soft bases like sulfur.